We're not doing a U-substitution yet. Yeah, okay, so let's do 1 minus cosine squared x sine x. Ah, okay, no, not yet, not yet. We need one more, exactly. So now, though, what do you see? U is, yeah, now you can see, if you said U is equal to cosine x, we're going to have du is equal to negative sine x dx. So dx is equal to negative du over sine x. So now does it work kind of nicely? Yeah, you have 1 minus u squared over u to the 6th times sine x times negative du over. Does the magic now happen? Yeah, the magic, our friend, it's gone. So we have sine is sitting right there, and the magic, the really cool thing happens. It's gone, leaving with negative of 1 minus u squared over du. Now the question is, how do you go about integrating this? Now it's just breaking it apart into u to the negative 6 du plus the integral of u to the... What am I doing wrong? What I'm doing? Don't doubt me. I'm actually on fire. On fire. I am okay. No, it's not minus. No, it's not. I distributed the negative. Haha, I'm right. So we looked at this and we said, okay, it's not trig, it's not a rational function. We tried parts. Parts doesn't work because it gets back to the exact same place you got before. So what happens if I just said, what was the original one? We'd like to do this, right? So what was du equal to? 1/2 x to the negative 1/2 dx. So what does dx equal? 2x to the 1/2 du. Is that correct? Is that correct? I'm okay, okay. But here, I understand, we're going to have a problem, I understand, but we're going to see if we can get through the problem. It's e to the what? E to the what? E to the u, right? But instead of dx, what do we write? 2x to the 1/2 du, right? But what does x to the 1/2 equal? Oh, look at this. X to the 1/2 is right there. So what do you end up with? You're still not done, kids. You're still not done. You end up with 2 e to the u times what? I put the 2, so it's u du. I put the 2 out front. So you end up with 2 integral of u e to the u. And now you think to yourself, man, we didn't really change much. But did you? Yeah, you did. Because now what can you do? Now you can use what? Now you can use parts. Now parts works. Isn't that cool? So here, it was creative substitution. You did it once, and you ended up with the same thing you already had a U-substitution for. The base is small, that's right. Since we have a target already, what's this integral going to be? It's going to be x to the 5th plus 1 all over x times x squared minus 3x minus 10. So you end up with the integral of x to the 5th plus 1 over what? I'm just asking. X plus what? X plus 2. So you do this, and then you'd ask yourself something that's going to get us to a wall, which gets us to what you want us to do. I understand what you're seeing out there, but my point is, that's what most people would naturally do. The challenge, though, is, what's the power of the top? Bigger than the power of the bottom. So are we going to be able to partial fraction decompositionize this one? Is it going to work? Not really. You're not. So what do you need to do to this one? You have this one. You theoretically, look. You would want to aim for something like this. You'd want to have x to the 5th plus 1. Sorry, excuse me. No, it isn't. But I'm just showing why you run into this wall. You're looking to turn it into a over x plus b over x minus 5 plus c over x plus 2. And can you really do that nicely? Not really. Not in a helpful way. You try and you get really sad. So instead, what are you going to do? You're going to take x to the what? X to the 3rd minus 3x squared. Was it plus 10x or minus 10x? Into what? X to the 5th plus 0x to the 4th plus 0x cubed plus 0x squared plus 0x plus 1. So now you have, no, x squared. Get x to the 5th minus 3x to the 4th minus 10x cubed. Biggest mistake by far is forgetting that you subtract the entire thing. 3x to the 4th plus 10x cubed plus And now you have plus 3x. So you have 3x to the fourth minus 9x cubed minus 30x. And you subtract all of it, so you get 19x cubed plus 30x plus uno. So then you have plus what? Plus just 19 actually. You get 19x cubed minus 57x squared, right? Minus 190x. Oh wait, hold on. That's a squared right there. 100 and sorry, plus 0x. Sorry, I did it too early. Sorry. 190x. Yeah, I know. I'm sorry. Subtract right there. So what are we left with? 87x squared. This is irrelevant actually, but you'll see why in a sec. Plus 190x, right? So what do you end up with? This fraction is equal to what? Plus 1. Yes, you're absolutely right. X squared plus 3x plus 19 plus 87x squared plus 190x plus 1 all over what? Cubed minus 3x squared minus 10x. So now we do well, hold on. Now you have the integral of this thing right here, and the front part is straightforward integration. This one you are happy, you're like, yay, I can integrate that. But then what do you have to use right here? Partial fraction decomposition on that one. Now you can do a partial fraction decomposition. Now you can. This one does work. It's just u equals ln x, and then you are happy. You are very, very happy. Thing. Well, kind of. We need to do something first. First, we're looking at, we want to manipulate what's in the middle. So let's take this right here. We're going to change it into root 1 minus x over root 1 plus x. What do we want to multiply by? Anybody want to take a guess? Yeah, kinda. I want to do this instead. What do you think? Yeah, I want to do this. I want to do this instead. So what does the numerator become if I do this? Oh, excuse me. I typed it wrong. Sorry. This is what I mean. Sorry. So what does the numerator become? 1 minus x, right? The square root of a times the square root of a is a. What does the bottom become? Yeah, it becomes the square root of 1 plus x times 1 minus x. But what is that going to be? 1 minus x over what? 1 minus x squared. And how many integrals? Oh, I see 2 of them now. 1 over the square root of 1 minus x squared dx and plus what? Plus x. Yeah, it's minus. Thank you. No, it's okay. Minus x over dx. Exactly. So I see something. Well, what's this? What is that? Come on, kids. What is it? Help me. What is it? It's sine. Sine inverse. That's just sine inverse x, right? Huh? I got independent confirmation from the back. And then what do you have to use to do this one? Trig sub? Do you need trig sub?
No, you have a u.
You can just use u, right?
Yeah.
What's u going to be on this case? What do you think u should be? How about 1 minus x squared? Because now you have du is equal to negative 2x dx. So dx is equal to du over negative 2x. So now you have, not plus, I'll change it back here, minus. Oh, because it's going to kick out and turn into a plus, you're right. So I was lucky enough to do it right. So it's going to be x over the square root of u times over 2x. We're to kick the negative out. So now we have, and then we'll do plus. Well, we haven't integrated yet, but there will be eventually there. So we have sine inverse, and it's being really loud. Okay. Stop spelling error. That's nice. Shh, kids, regroup. Are we okay? Is that correct? I think that's good. So we end up with sine inverse of x plus 1/2. It's going to be u to the, but then we have to put a 2 out front, right? Plus c. Yep, it cancels. So now you have sine inverse of x plus, what was u? 1 minus. It was 1 minus x squared. to the 1/2 plus c. So most likely on the test you'll see it written like this, not equals, plus the square root of 1 minus x squared plus c. That's what you would see the final answer. There was, exactly. And here's the thing. There's a little bit of intuition you can have about improper integrals that sometimes is good and sometimes is very, very bad. Okay? So let's say I was asking you about this function right here, y equals 1 over x squared. And let's say we're just looking at the first quadrant. So if I were to graph this and just look at the first quadrant right here, you'd end up with a function that looks like this. Now, if I asked you to find the area, let's go from here. Let's say that's x equals 1 to, let's say, x equals 2. Is that something you could do? Could you find me the area under the curve from x equals 1 to x equals 2? Sure. You can integrate 1 over x squared and then evaluate at the endpoints, right? Not bad. Now, here's what we're going to do. What happens if instead of having a boundary over there, I say we're going to do this integral instead? We're going to do the integral from 1 to infinity of 1 over x squared dx. The first type of indefinite integral we're going to look at are ones that have infinite limits, either in one or both slots. So when you look at this, what does that say? What are we doing? We're finding this area. And how far over does that go? It goes as far as you want to go, right? So what might be your guess as to the answer to this integral? You might think it's infinite, right? Because it goes infinitely over. So maybe that means that it adds up to an infinite area, which certainly, which certainly can happen. But what else might you think? It's getting infinitely close, so maybe it's getting close fast enough to counteract it, right? Something isn't infinite if it has a boundary, right? So if I go halfway to the wall and halfway to the wall and halfway to the wall, I'm never going to get to the wall, but what am I going to get infinitely close to? The wall. So the limit of that operation is the wall. No, it's purposefully straightforward. So the point is, how do we do this? Well, what you can now do is this instead. You can say this right here is equal to, and that's a bent arrow, just to be clear. This is equal to the limit as t goes to infinity of the integral of 1 to t of 1 over x squared dx. So what we're doing instead is we're looking at it as we move the boundary over, what happens to the overall area. So instead of going from 1 to 5 or 1 to 6, you do it and you look at it as a limit and just see what it looks like. So what happens when we integrate this? Well, you can integrate it. What's the integral of 1 over x squared? It's going to be negative x to the negative what? Negative x to the negative 1, right? Because you drop the negative to the front, it becomes 1 over x squared. And now we're going from 1 to what? 1 to t. So that's going to be negative t to the negative 1 minus negative 1 to the negative 1. And all of this is, what's in front of this? Limit as t goes to. So this is the limit as t goes to infinity. So now let's look at it and see what happens. Now we have the limit as t goes to infinity of 1 over, oh, negative 1 over what? Is it plus 1 or minus 1? Be careful. We have minus negative 1 to the negative 1, so that's minus 1 over negative 1. So it's going to be plus. Better be, right? So what do we now have? We have the limit as t goes to infinity of 1 minus 1 over t. What does that equal? 1. So guess what? If you go from 1 to infinity of this integral, it's always less than. It gets infinitely close to 1. It's infinitely close to 1. And there it is. You just evaluated your first indefinite integral. So improper integrals. Here are the 3 types, or the 3 things we need to worry about here. So the first thing is what we just did. This allows us to take an this integral with that's an infinity up there. You can't really see it. And instead, you can pull the limit out to the front. That's what we did. That's what we did. Another thing here is that if it exists, then if it goes from negative infinity to b, finding that area is the same thing as going from, let me zoom in right there, hold on a sec, so you can see it. There's one very, very similar to what we just did. So this one says, determine whether the integral from 1 to infinity of 1 over x dx is convergent or divergent. Give that a try. So if you do this, you have to write this out first, at least in this case. You're looking at the limit as t goes to infinity of the integral of 1 to t of 1 over x dx. So that's going to be the limit as t goes to infinity of ln of what? ln of x from what to what? 1 to t. So that's going to be the limit as t goes to infinity of ln of t minus ln of 1, right? What's ln of 1? So you're looking at the limit as t goes to infinity, and you can take the absolute value away because you're going to positive, ln of t. And what's that equal to? Yeah, it's getting infinitely large, so this is divergent. Overthought here? Where do you want to break it across? Does it matter? 0, right? So you're looking at doing negative infinity to 0 of 1 over 1 plus x squared dx, right? And you're doing 0 to infinity of 1 over 1 plus x squared dx. And we know that's going to turn into the limit as t goes to negative infinity of t to 0 of 1 over 1 plus x squared dx plus the limit as t goes to infinity of 0 to t of 1 over 1 plus x squared dx. But what is it going to be for each of these? It's the limit as t goes to negative infinity of what? Tan what? Tan inverse of x from t to 0. And this is the limit as t goes to infinity of tan inverse x from 0 to what? 0 to t. Is that correct? Okay, let's try it. So you're looking at the limit. I'd say pi. Okay, I like that. I actually like that a lot. Negative infinity. You just want pi to come out. You actually want pi. You're Cartman. Okay. Hold on. Just hold on a sec. Hold on a sec. It's tan inverse. Give it a second. Of tan inverse of 0 minus tan inverse of t plus the limit as t goes to infinity of tan inverse of t minus tangent of tan inverse of 0. What's tan inverse of 0? What is it? 0. Thank you. I'm just going with it here. 0, and this is what? 0. Oh, wrong one. See, it does matter if I'm sloppy. Yeah. So it goes to 0. So you end up with the opposite of the limit as t goes to negative infinity of tan inverse of t plus the limit as t goes to infinity of tan inverse of t. So the question is, what does this look like? What is tan inverse? So the question now is, you have negative tan inverse of essentially negative infinity. I'm putting that hazily in there. I know, you don't like seeing that, and it kind of makes your eyes hurt. Tan inverse oscillates? Right. So look, you have to remember what the graph looks like, kids. So here's your graph. No, exactly. I know what you were thinking. It's tangent. Yes, it is. But tan inverse, you flip one of them to get the inverse. You did get your pi, and I will give you a gold star. How about